that specify called the value semantics of lambda calculus. So here is the straightforward application rules, two of them, and the last one is the substitution into the actual call. Right? The way you can encode them, these inference rules, I always tell my students that logic programming is not very different from inference rules. All you have changed is notation. Okay? That is, of course, you know it's a lie, but that will cover for the first approximation. Right? So here is the encoding in Prolog, the same rules, and it's a reasonably straightforward encoding, as you can see. The only thing that is not completely given here is how the substitution is handled. Right? So everything else is completely encoded here. And this is actually the executable specification. Once this encoding is complete, you can actually give a query and say, what is the small step semantics for a single term, and the program should evaluate this query and come back with the next term. You can turn this small step semantics into big step semantics by simply doing reach over this. Okay. So this is a reasonably straightforward way of encoding logic programs, and this is a standard way of encoding semantics. So what happens with substitutions? Actually, there's a neat thing that you can do with substitutions. So this is the one part that I was missing in the semantics slide in the last slide. You can see that if you take open up any book on this kind of treatment, they will give you a simple recursive definition of inductive definition of what is substitution. And this is how the definition will look like. This definition, unfortunately, is not complete because it assumes somewhere along the way it assumes alpha conversion. Because in this rule it simply says that you can do the substitution only if y and x are distinct, and y doesn't occur free in S. What happens if y does occur free in S? Then you're supposed to rename y appropriately, and that is not actually covered in this. So there are two ways to encode this. Either we can actually program alpha renaming explicitly, that we can take this term and whenever we apply this, we check if y is actually free in S or not, and if it is not free in S, go ahead and change the name of y, right? So you can rename lambda yt into lambda y prime and substitute the properties of y and t appropriately. You can invent fresh names, you can use Jensen or some way of programming this. Or actually there's actually a trick that you can play, that if you have a suitable restriction on how your lambda terms look like, that is, at least in the initial stage, you can assume that every lambda term that you would write down will be written down in some kind of definitional format instead of actually having a lambda term nested. Each lambda will be taken into a separate definition, and this lambda will be a parameter to the name of a function. And then what you can have is restrictions saying that every variable, and these names, the parameters to the functions, can be modeled as logical variables. And you can say every variable occurs uniquely within the definition of a function. That if there are multiple variables in the function, they are all named separately. And that's the initial lambda term that they are given. And then when you apply the reduction rules, standardization that happens when you do resolution will automatically take care of conversion. So you don't need to actually do manipulation of substitutions, you don't have to manipulate names, you don't have to do anything else. And this is actually a very neat trick that you can play. It is actually just a trick. There's nothing deep to this. It is just a trick. But this trick actually gives us a lot of power, and it turns out that when we try to encode the semantics of pi calculus, where names flow all over the place and it's actually hard to handle exactly what scoping of these names are, it turns out that this trick actually plays a very useful role, that we can actually encode semantics of pi calculus very, very simply as a logic program using this trick of using logical variables as names for pi calculus names. Okay? And this enabled us to build a model checker for pi calculus, one of the first ones in 2003, and this system we moved along after that. So that is one simple semantic rule encoding. A similar thing happens when you try to encode abstract semantics as well. This is a 4-rule system for what is called May points to analysis. This was developed by Anderson in '94. This does what is called flow insensitive, context insensitive points to analysis for C programs. So in this case, what we are assuming is that you take a C program, you throw away all the control structures in a C program. You assume that your control can flow all over the place. Any statement can follow any other statement, and you can reduce all the assignment statements in C to one of 4 forms. You either take the address of a variable, or you can assign one variable's value to another. You can dereference a variable and assign its value to another. You can take a variable's value and assign it to a dereference location. Right? These are only 4 things that happen in C. And now we can figure out which variables in your program may point to which other variables, which locations. Right? Here these rules are themselves straightforward. And if you can see, for instance, let me take a rule like this. It says when you assign, if there's a statement in the program with the form P is star Q, I can conclude from this statement that P may point to S if, before the statement is executed, I have concluded that Q can point to R and R can point to S. If Q points to R, now star Q will be actually R, and now if P is assigned to R then, and R is pointing to S, P points to S. Right? This is very straightforwardly encoded in Prolog. Points to of PS is simply false. Right? Again, there are 4 inference rules on the left side. There are 4 logical rules on the right side. Okay, this is straightforward. Again, you can use this for evaluating points to information in C programs. Right? I wish the story were as simple as this. It turns out that since this program, you may have one statement that says P is assigned Q, and another statement that says Q is assigned P. You have cycles in your inference, and you need some way of stopping inference over cycles. And of course, if you either do bottom-up evaluation or do semi-naive or you do tabling, you can then terminate on this. Right? This is simply a data log program. But again, this is kind of old technology. In 2001, there was a PLAI paper by Nevin Hinze and co-authors on doing points to analysis, but instead of computing the entire model, only computing the points to information for the relevant variables. Because there are points, there are places in your program optimization where you want to only ensure that this variable X that I'm trying to somehow store in the register or throw away is not pointing to anything else. Okay? So this is called demand-driven analysis, and there was a paper on demand-driven analysis in PLDI. If you did table evaluation for the last 4 rules I showed you, you automatically get some kind of demand-driven evaluation. Right? You've got this query goal-directed. But even though it is goal-directed, we have clauses like this, for instance, here. If you do it naively in tables, what happens is, if you are asking what are all the places this R can point to, the very first thing that happens on the right-hand side is you look for all statements in the form star PQ. There's no relationship to PQ to R. So you lose all your goal direction the moment you execute the right-hand side. Right? So again, we can play a trick. Again, no big deal. Change your program around to have both points to and points to by information, and you can calculate the whole thing goal directed. And this was essentially the essence of the PLDI. And we can now say that in one slide, that this is the thing. And that's the kind of cool thing about doing inference or encoding driven logic. So far what I have said is things that you can do otherwise, that you can do simply or more elegantly in logic. That's fantastic. It makes us happy to see that we can encode it elegantly, but what more can we do with this? Okay. It turns out that, it turns out that there has been also work in directed database community and logic programming community on incremental evaluation. So given a query, given query answers from the last time you ran this query, if some of the facts or rules of your program change, how does your query answer change next time around? Right? View maintenance, the so-called view maintenance problem. So we thought that now that we have encoded everything in logic, maybe we can just use view maintenance algorithms that we knew about and automatically essentially get incremental program analysis from this. It turns out that view maintenance is kind of a solved problem on paper, but at least 10 years back it was not a solved problem implementation-wise, and even now it is not completely integrated within these systems. So the history of view maintenance was that there was an algorithm called DRED, delete redirect algorithm, that was published in Sigma 3. This is for data log programs, definite programs. The way this was motivated is, it turns out if you do semi-naive evaluation, it's automatically incremental for additions. If you add a new fact, you can very easily compute deltas and compute your changes in your answers. And it's rather straightforward. What is not straightforward is what happens if your facts are deleted. Right? Because the same fact can have impact on multiple answers, or there may be multiple ways a single answer can be supported, therefore even deleting a fact doesn't change it. So you have to do a little bit more processing when facts get deleted. And that is the whole idea of the dered algorithm. If you do a delete, what they do with that algorithm is to go and mark up every query answer that could be affected by this deletion, and go ahead and delete them and try to rederive them again. That is dered. It turned out, surprisingly, that there are two parts. One is that dered turns out to be prohibitively expensive. It is just impossible to implement in any reasonable way. And the other that turns out for dered is very similar algorithms for dered were published in two other communities. One for model checking. There was a work by Sapolsky and Smolka in CAB in '94, basically a year after dered. And there were also works on program analysis by Ure and Landy and Ryder in ICSI 97, ICSI 98-9 on doing essentially dered in a different setting. Okay. And they were all roughly the same, that whenever the underlying facts are deleted, you go ahead and make a mark on everything that was dependent on this deleted facts, and then go and try to rederive. That's the whole thing. But we can actually do better than dered, and there are a few results that we got that were published at ICLP that actually tell you how to do this a little more effectively. The first result was to use some kind of an intermediate data structure that is computed and stored at the time of query evaluation that you can then use to go and mark up which goals are to be deleted or which goals are to be marked. The second thing is to say that whenever I propagate a mark, I don't have to actually have to find out all dependencies of a single deleted answer. If a fact was used in deriving an answer for the very first time, that I will call as a primary support, and if the primary support is deleted, then I will have to suspect that the fact is gone. As long as the primary support exists, I know that the answer is correct. I know that the answer is still correct. So there were two improvements we made. The first one, keeping track of the dependency information in terms of graphs, and also marking certain supports as somehow special. Right? So in the first work, we just marked the very first support as special, and later on we realized that the first support has nothing special to it. Actually, any acyclic support would be sufficient to keep track of. And the downside of this work was the space consumption, that this intermediate graph that we built can be significantly larger than the amount of storage that you would normally otherwise store in tables. The space complexity of using support graphs for evaluating logic programs is roughly the same as the time complexity for evaluating programs, which is not useful for things like program analysis. So we devised a different structure called symbolic support graphs, try to store them in a more compact way and figure out what the supports are on the fly, and then subsequently handled updates, and later on there was also work on extending this. This was all for definite programs, pure programs, and later on we extended it to prologue programs. And the difference between the works here that I said about definite programs and prologue programs is that for definite programs we kept track of dependencies of every answer and every fact. For prologue programs, instead of looking at answer dependencies, we are looking at call dependencies. Because the answers could be computed in any other way, so at least just keep track of the calls, and if any call that depends on a deleted fact is affected, reevaluate the call. Roughly that. And this is what has been implemented later on in XSD, and has been significantly improved upon since what I wrote here. So now we have an incremental, now that we have an incremental evaluation part, it turns out that we can actually use this incremental evaluation to go ahead and look at program analysis and the same points to analysis and look at incremental evaluation of points to analysis. We can do incremental evaluation of model checking algorithms. Okay? All that has become automatically incrementalized by simply keeping the incremental part the core inference engine rather than making each algorithm, the model checking algorithm or program analysis algorithms. So now we have two interesting advantages of using logic programming and coding. One is that it's kind of elegant. It is something that makes us happy. And the other is that we can actually do things that could not have been done otherwise. Or was much more difficult. Okay. So the same thing is what we did earlier on as well. This is the semantics of what is called the temporal logic of computational tree logic, CTL. So this logic is the one where models of this logic are given in terms of runs of an underlying transition system. And there are formulas in this logic like propositions that hold in various states. You can have conjunctions of formulas, and you have temporal formulas of the form, for instance, EF. What EF says is that EF says exists a path where finally phi holds. So abstractly speaking, what this means is if a property F has to hold eventually or on some path, that means there is some state that you can reach from S through 0 or more transitions. And once you take 0 or more transitions, you get to T. And in T, F holds. Right? The property F holds in T. So if from S you can reach a T where F holds eventually, then you know that there exists a path from S where F holds eventually. That's the semantics of EF. Similarly, there are other temporal operators like AF, always in future something holds, and similarly kind of global properties and properties like exist globally, that in a path, at every point along the path some property holds and stuff like that. You can write down these properties in CTL. I'm going to give a fragment of this. This can again be written down as a logic program, and this is essentially a model checker now. Now if you evaluate it, the query evaluation over this logic program becomes a model checker for CTL. Right? And there is nothing, this is very similar to the kind of straightforward encoding that we did for points to analysis. The only thing that this needs above and beyond Prolog is tabling, that you need to make sure that if there are cycles in your underlying structure, the proof doesn't actually follow along all the cycles. Your proof will be able to actually detect the cycles and stop it. So along these lines, we have done a number of model checking work. The interesting things about here are infinite state systems. There are different classes of infinite state systems. Things like real-time systems, which Belzano and Podolsky did in TACUS 98, I think. Gopal Gupta and Enrico did real-time systems with CLP in 99 RTSs, I believe. I don't know exactly the dates, but it's RTSs. So those are one class of infinite state systems. So far, the inference rules that I've given you are plain data log-like inference rules. If you add constraints to them, you can actually take care of real-time systems like that. You can also do infinite state systems that come up by calculus, where the space of names that a program can go through are unbounded. You can also look at infinite state systems where the data values are actually over a domain that you don't know about. And this is actually an interesting result that again comes out of a very simple logic programming trick. If you think of a system like, let's think of a very simple data link layer protocol. There's a wire that runs between 2 points, and you keep sending data back and forth along that wire. Let's think of alternating bit. So there is some kind of control part of this protocol, that you send a bit and you mark the bit as with some number. I'm sending packet number 0 and sending packet number 1. And acknowledgements come and say packet number 0 was received, packet number 1 was received, and stuff like that. That's the alternating bit, right? But what about the payload? I want to make sure that every packet that I send out is received in order. If I have this kind of property, I need to know how many different packets do I need to distinguish. Right? So if I'm sending packets in a line, and if I want to find out if packets are being received in order, it turns out there's a theorem by Walper from '87 that says for this kind of a simple data link layer packet transmission protocol, I need to distinguish between 3 packets. The 3 packets are the packet that I sent first, the packet that I sent second, and every other packet. So every other packet can be abstracted into a single value. And the idea is that I say whenever I send 1 and then I send 2 later, I receive 1 and 2 in that same order. Every other packet has been abstracted to a new value called 3. And for every protocol, we need to do this abstraction separately, and we need to calculate how many different numbers we have to give in order to figure out whether in-order delivery of packets is assured. But it turns out when you do it in logic programs, if you just leave the payload uninstantiated as an uninstantiated variable, you can simply have equality and disequality constraints and be able to get the minimum number of packets that you need to distinguish automatically. The proof system will automatically not ground your packets with that value, and all you need to know is whether I can distinguish between packets or not. So it will turn out that you will have only three kinds of constraints. If you have send packets x, y, and z, you have constraints in the form x not equal to y, y not equal to z, x not equal to z, and that is sufficient for finishing your proof. Okay. So data independent systems fall very neatly out of the whole thing without doing any changes. I can essentially take the same CTL model checker. Here I have assumed that my transitions are S and T. I didn't say what the transitions look like. They need not be atomic. They can contain variables in them. They can contain constraints in them. Right? And when they contain variables in them, and if I have disequality constraints, I automatically get data independence here. Right? So this is the idea that once you encode it in logic, there are various tricks that I can play. I'm again calling them tricks because there is really not too much depth here. Right? It's not a new semantics. It's not a new logic. It's nothing new. It is techniques that we know and love, and when we program in Prolog, we use them all the time. It is as simple as that. The parameter system work is slightly different from orthogonal logic programs. The idea here is if you have a concurrent system composed of multiple components, you want to verify some properties that hold for the entire family, independent of the number of components in the family. So one example of this kind of parameter system is a kind of locking protocol. You have a number of objects in your system, you have a number of threads in your system, and you want to make sure that your protocol works irrespective of how many objects there are, irrespective of how many threads there are. This is clearly an infinite state system if you just model it like that, or you can model it as a family of finite state systems. And there are methods for verifying them. It turns out that, again, work on parameter systems, there is a lot of kind of theoretical abstract work, but implementations are few and far between because taking those rules and implementing them and getting results out of it is kind of difficult. But now that you have a logic programming technology behind, we can actually write down parameter systems, we can write down verification systems for it. They are a little more complex than a simple one-page CTL model checker that I told you, but instead of a one-page, it's a 4-page program. Right? Again, we know how to do that. So this side is all the model checking stuff that we have done. Logic programs have also been used for program analysis that I told you before. We have also used them for looking at security policy analysis. The questions are roughly the same, that they are kind of reachability kind of questions over some state space. So my main focus today is going to be on probabilistic systems, which is kind of a new work, and I'm going to take the rest of the half hour talking about probabilistic systems and how we can actually leverage logic programming technology to verify probabilistic systems. Again, my basic idea is going to tell you the basics of probabilistic systems, the kind of straightforward way of encoding model checkers for probabilistic systems using existing techniques, and then we will see what more can we do now that we have encoded in logic. Is there some advantage that we get out of it? So how do we do, what is probabilistic logic programming? How do we encode probabilistic systems as logic programs? At a very, very rough level, you can think of inference in logic programs as something like this, that you have a bunch of rules or con clauses, the programs, you have a bunch of facts that the programs work over, and you look at answers that are entailed by this program. Okay. That's our normal method of looking at logic programs. Now let us say the facts themselves have some measure of probability. It's not simply uncertainty that we don't know what facts are true or not, but we have some kind of distribution over these facts. Okay. Now what we can do is, the same entailment relation, we can compute a distribution over the answers. And this is the overall idea of probabilistic logic programming. That if we have facts that are kind of fuzzed out with the distribution, the answers themselves are fuzzed out there, kind of induced distribution. And now what we want to find out is exactly what this induced distribution looks like. Okay, and that is the inference problem. This is roughly the approach that is taken to probabilistic programs by a language called Prism. Prism is Taisuke Sato's system from mid-90s. It's a language as well as a system that is reasonably well developed. It is, and there are a number of other systems that are competing with Prism and maybe better than Prism in some ways. I'm going to choose Prism because the underlying way in which Sato adds probabilities to logic programs is something very simple and straightforward and easy to understand, and so I will use this method now. So what Sato-san did is, just like logic programs have a usual set of rules and facts, he introduced a new set of facts called MSW. You can think of them as facts, but these are essentially facts that have a distribution. These are probabilistic facts. There are three parts in an MSW. It's kind of special. The first argument, X, is a random process that produces values. And for Prism, this is a discrete valued random process, finite discrete valued random process. The I here is supposed to be the instance number, so you can think of this as like this. That X is a coin that I'm going to toss. I will name this coin. I will say coin 1. So coin 1 that I'm going to toss. If I toss it 3 times, I will have 3 instances of the toss. And the outcomes of these 3 tosses are the random variables that I get, and those are captured by logical variables here. That's it. So every fact has 3 parts: the random process that will actually generate values, the instance of the random process that I'm going to use to generate values, and the value that I actually generate using the random process. Okay. And the assumptions behind this are that the random variables are all IID, and distinct random processes generate independent random variables and stuff like that. And there's a very neat semantics called distribution semantics that Sato gave that seems to give a very, very firm foundation for probabilistic programming that I'm going to use. We'll start with a very simple program. Here's a coin that I have. I call it A for simplicity. There are 2 tosses I'm going to do with this coin, A, 0 and 1. And I'm going to succeed in P whenever the 2 tosses yield the same value. Okay? Here, instead of calling head and tail, I'm calling it true and false. Right? So the labels are here like this. A is a coin, so these are the annotations that I have in this program. A is a coin that has values true and false. These are the 2 outcomes of this coin, and the distribution of these outcomes is given by this. You can change the syntax of it. If the syntax is not, if you're not happy with the syntax, you can move it around. But the basic idea is that there are facts that have values that are generated by a random process. Okay? Now, how do we give meaning to this kind of program? It turns out that you can treat these MSWs as though they are true in different words. You can construct different words based on outcomes of these random processes. In this case, there are only 2 random process trials that I'm going to do, 2 trials of the coin A, and they have 2 outcomes each, so there are 4 total words, right? And in each of these words, I'm writing down what outcomes I got. So the first word is that I tossed coin A. The first toss of coin A gave me true. Second toss of coin A gave me true. Right? So these are all the possible words. And each of the words I can associate a probability with this word by looking at the annotations of exactly what the distribution of these random variables are. So according to this distribution here, the chance that both coins land up in true is 0.09. I can annotate each of the words in probabilities. But more importantly, if I look at each single word, these just look like facts. There is no probability for this fact. In this word number 1, A0 is true, A1 is true. There is no other value for A0 and A1. There is no probability, there is no measure, there is nothing else fuzzy about this. So now if I consider this word and the set of rules I have in my program, that constitutes a simple, non-probabilistic logic program. I can now evaluate the usual model for this program. In this case, since it's a definite program, I will simply get a minimal model, and that will tell me what over the model. So there's a distribution over the words, there's a model for each word, and now I get a distribution over the model. This is the simple distribution semantics. So distribution semantics for a probabilistic logic program is simply a distribution over the models of this program. Okay? Instead of, for a definite program, the semantics of a definite program is a model, semantics of a probabilistic definite program is a distribution over models. That's a simple extension. Right? This is the reason I'm using Prism, because the extension is actually rather straightforward and easy to state and understand in 5 minutes. There are a number of other works on probabilistic logic programs, so I'm not going to say that others are any poorer. It is simply that the semantics are a little more complex, but it turns out that there are at least 3 different what look like independent and interesting proposals for introducing probabilities with logic programming. These turn out to be all based on this so-called independence choice logic of David Poole. One is Prism that I just explained. There is a language called Problog from the Leuven group, and there was another language called LPAD. And it turns out that all of them have essentially they are equivalent semantically. So any program that you can encode in Problog, you can encode in Prism, and vice versa. At least semantically. The evaluation techniques that they use are very different. So the systems that are built on top of them may have different powers, but the underlying language has the same semantics. Okay. So what are the systems? How does Prism actually evaluate programs? Now I'm going to switch to a slightly different example. Here we have, this looks like I call it a finite dimensional model. You can think of it as a Bayesian network with two variables A and B. A is a parent of B. Or you can look at it as a logic program where you say, toss a coin A, based on the outcome, choose which coin to toss next. There are two B coins and one A coin. Toss a coin A, if it turns out to be true, take the true B coin and toss it. Okay? And the outcome of that toss is the outcome of this entire predicate. And the way that this program is going to get evaluated, there's of course a distribution semantics to this. You don't want to enumerate through all the words. You want to evaluate them in a slightly different way, and you can actually do this in a goal-directed fashion. So think of an answer Q of t. So I'm going to write down the explanation for an answer. You can think of an explanation as a derivation of that answer, a derivation that actually means to do. So if I look at Q of t, how is Q of t derived? There are two possibilities on A. A can evaluate to true or false, right? So those are the two branches. There are two different explanations. But if A evaluates to true, A0 evaluates to true, I'm omitting the instance numbers here because I'm not tossing the same coin multiple times, so we can omit that. If A evaluates to true, then I take B of t coin and toss it. And in this case, if I want to evaluate the whole thing to t, this B of t better evaluate to true. Right? So that's one derivation. So I can make a tree of all the derivations. And I can start annotating this tree with numbers. Since the likelihood of A, the probability of A evaluated to true is 0.3, I can write down the probabilities of each of these outcomes on this branch. If the random variables used in any one of the explanations are all, they are all independent. A is independent of B and so on. Remember, Prism's basic assumption is that all distinct random variables are independent. Right? So if the random variables used in a single explanation are all independent, I can take the probabilities within the same explanation and multiply them together. That gives me the probability of the entire explanation. The same way with the other one. And if the random variables used, if the two explanations that I have are pairwise disjoint, are mutually exclusive, then I can simply add the probabilities of the two explanations. So that's the overall assumption. So the assumption is that we have random variables within a single explanation. They are all independent. Explanations are mutually exclusive, and did I do something? So now we can compute the probability of an answer based on the sum of answers, sum of the explanations. So this is Prism's way of evaluating this. So there are assumptions that Prism makes, and this is exactly what distinguishes between the algorithms that are used in Prism as versus the algorithms used in Problog and LPAD. So let me skip over the slide. It simply says what I said before. So there are these three assumptions that Prism uses: the independent mutual exclusion. The finiteness assumption I didn't tell you very distinctly. It is that every answer should have only finite number of explanations, because you're going to try to add the probabilities of explanations. So in order for that to be computable, you want the number of explanations to be finite. And Prism does this without materializing explanations directly. And it turns out, if you encode your statistical model just right, you will actually get inference that will mimic the underlying statistical model's best known inference algorithm. For instance, there are ways of encoding HMM, the hidden Markov model in Prism, and it turns out if you do inference over that hidden Markov model in Prism, you will get essentially the Viterbi algorithm. It will have exactly it will mimic the actual Viterbi algorithm. This is important. So we want to use logic programming not just as an encoding tool for semantics. We want to actually make it executable. And we want to build model checkers on it. We want to build analyzers on it. We don't want to simply say that here's a logic program that does this analysis, that embeds this analysis, this logic, and thank you, bye-bye. We want to actually do something more with it. So we want to make sure that evaluation is efficient. So this is an important aspect. The languages like Problog and a system called Peta that Terry Swift and Fabrizio Ribisi worked on a couple of ICLPs back. They use a slightly different way that instead of computing these numbers, instead of assuming mutual exclusionary independence, what they do is materialize the explanations in some way. And the clever trick that Problog introduced is to materialize explanations in terms of a BDD, in a binary decision diagram. You can think of each MSW or a random variable as a Boolean variable, and outcomes as different outcomes as a Boolean variable. And you can build a BDD out of it. The idea is that once you have a BDD, each path through the BDD will have this independence and mutual exclusion assumptions holding. So now we can compute probabilities based on the BDD. So it's a very, very clever trick. And but in terms of model checking, it's still not sufficient because we will still have finiteness assumption. That we want to make sure that every query answer has only finitely many explanations. So now that we know a little bit about what is probabilistic LP, I will give you a brief, quick idea of what we do with model checking with them, so we have in probabilistic systems the most favored way of modeling probabilistic systems is called Markov chains, that most of you know. There are also Markov decision processes where at each state you have choices to make, and each choice will lead you to a distribution of states that you can go through. There are various kinds of schemes that are the formalisms that people have come up with. Similarly, there are temporal logics for specifying properties like PCTL, which is a simple probabilistic computation tree logic, to something more general than that. There are a number of model checking systems as well. There is a model checking system called Prism. It looks like whoever works in probabilities will want to name their system something starting with PR, and there are only a few words that will actually spell out nicely with the PR. So, this Prism system is not Sato-san's system. It is by Marta, Quaid, Koska, Oxford. And there are a number of other model checking systems. What I mean by probabilistic systems here is very different from, there's a kind of orthogonal line of work called statistical model checking, where you take a non-probabilistic system and try to do some kind of sampling-based model checking to give guarantees on how likely is this probability going to be hold. Okay? And that is simply to combat the state space exclusion of a non-probabilistic system. This is, we are in contrast, we're going to look at systems where the probabilities are in the system itself. So it is not simply a statistical technique for estimating whether a property holds or not, but it's a technique for inferring what likelihood of what is the likelihood of a property holding in a probabilistic system. So here is a simple Markov chain. There are 5 states. There are transitions. The numbers on the transitions are probabilities. So what this simply says is, with 0.5 probability from S0, you go back to S0. From 0.3 probability, you go to S1. From 0.2 probability, you go to S2. And the encoding of this Markov chain in logic is again straightforward. That now that you have coin tosses in your logic, we can simply say from state S0, we will toss a coin, and based on its outcome, we will go to the next state. Right? So that's our transition. Now that we have these coin tosses, we can actually encode reachability. So we have encoded transitions here as tossing coins, and all we do with reachability is that we toss a coin, you go to the next state and keep going. Right? So if you want to look at reachability from S0 to S4, you can simply issue a query. Reach of S0, 0, S3. This tells you what is the likelihood of reaching from S0 to S3. We can read this kind of queries, and it turns out that if you encode this in Prism, Prism's underlying distribution semantics will compute the right answer. But unfortunately, Prism's evaluation is not going to terminate, and that is simply because there are unbounded number of explanations for why S0 reaches S3. Why does S0 reach S3? From S0, I can reach S3 by going straight to S3, or skipping 1 time in S0 and going to S3, skipping 2 times in S0, going to S3, and so on. Right? So you can see that there are infinitely many paths from S0 to S3. So what we need from here is actually a way of inferring slightly different. So neither Problog nor Peta nor Prism will actually evaluate this query successfully, but you can make an inference technique work over infinitely many explanations. And this was the work that we did in 2012. There's this inference technique that we gave called PIP, Probabilistic Inference, I think it was called. For a lack of a better, lack of imagination, we just called it PIP because it sounded nice. And what it basically does is it looks at each explanation and thinks of the explanation as a somewhat try to symbolically represent the set of explanations. And so what we have is in these infinite explanations is a sequence like this. So first explanation is that from S0 I went to S1, from S1 I went to S3. S0 I went to S0, from S0 I went to S1, S1 I went to S3, and so on. Right? So there are infinitely many explanations like this. So these just look like strings. A string over a finite alphabet. The set of strings is infinite, but the alphabet is finite, and there may be some nice property that I can use about this set and be able to represent this set compactly. Okay. That nice property may be simply regularity, or actually what we did is to represent this set of strings as a grammar. Okay. So it is slightly more general than simply assuming regularity. So the explanations are visualized in terms of a grammar. And if you can kind of beat upon this grammar appropriately, you can actually think of this grammar as a stochastic grammar. So the set of explanations for how you go from S0 to S3 is simply a grammar like this. If you can write it down properly. And it turns out that the guards on these grammars are tosses of the same coin at the same instance with different outcomes. So this is simply a stochastic grammar. And for a stochastic grammar, there is a well-known technique for evaluating the mass of strings produced by the grammar. That is simply writing down equations for this and saying what is the least solution to this set of equations. Okay. So we take this grammar that looks like this, write it down in stochastic grammar form, slightly different form of writing it down. But once you write it down in stochastic grammar form, you can say what is the probability of any string in this language? What is the probability mass of strings produced by this language? And that is just given by the least solution to this equation. Okay. And that is all we do. So the idea is to take explanations, represent them symbolically using some kind of grammar form, and then generate equations from them and solve them. So that was the work in PIP, and now we can actually model check CTL. Now we can actually model check probabilistic CTL. So I will give you a quick overview of PCTL and how am I doing in terms of time?
You have about 10 minutes.
10 minutes more. So I will give about 5-minute explanation of this model checking part, and at least 5 minutes I will spend on the current feature. So here is probabilistic CTL. This has very similar things as CTL, or you can even think of them as simple LTL formulas. You look at phi1 until phi2. You say that in a run of the system, property phi1 holds until property phi2 holds, until a stage where phi2 holds, and then you don't have an obligation to prove the phi1 anymore. Or next stage phi holds. So these are called path formulas. These are formulas for which the models are given in terms of runs of the system. And there are so-called state formulas where the models are given in terms of sets of states. And these are simply that property, some proposition A holds in a state, conjunction, disjunction of these kind of properties, or probability masses of runs that I can go from that particular state onwards. So I can say, for instance, probability of psi is greater than b, which means for paths emanating from this particular state, the probability that psi holds in some path along that from that state is greater than b. So this is called PCTL. This is a very, very popular logic for model checking probabilistic systems, for discrete time probabilistic systems. So here is a corresponding Prism-like program for it. So these are the state formulas. These are rather simple, right? A proposition holds at state S if you have a bunch of facts that say exactly what proposition holds in each state. And are easy. The more interesting thing is here that you say a path formula until S of 1, S of 2 holds at state S if the guaranteed until part already holds the state S, or you can make some transition, SF1 holds in the current state, and SF1 until SF2 will hold from subsequent states. Okay. So it's a very straightforward encoding of, very similar to the EF encoding that we did for CTL. And we can take this encoding of PCTL, now we have a model checker for PCTL. How good is this model checker? We checked it very quickly against Marta's Prism. Prism is a very, very well-developed system. There are numerous examples where Prism is used. Prism is a good system in a sense that it is used by people who didn't develop it. That's a mark of a system that has reached its maturity when somebody else takes it up and uses it and simply writes one acknowledgement saying, I use Prism. That's the way the Prism is now. It's very well developed, it's very well optimized, there are a number of things that go on with it. The reason for this chart is to say that here is a very straightforward encoding of PCTL semantics. Let us see how far away from Prism we are. And it turns out that we are about a factor of 3 away from it. This factor of 3 may be the most difficult factor of 3 to get to, the final optimization part, but at least this says that we can build realistic model checkers by writing them down in logic and evaluating them as a probabilistic method. So this is so far for PCTL. It's a simple enough logic to do this. There are actually more complex logics that we can work with. There is a work by Rand, Cleveland, Purushottam Iyer, and Murali Narasimha that appeared in TCS Theoretical Computer Science in 2005. They introduced two interesting things. They introduced a model called reactive probabilistic transition systems, and they introduced a logic for it called GPL, generalized probabilistic logic. Both of them are significant generalizations to the underlying models and logics that we had for probabilistic systems. The RPLTS, as it stands, basically what it does is adds labels to the transitions, and from each state there can be multiple outgoing labels, and there's a distribution associated with each label. So for instance, here from this state S3, there are two actions. There's an action you can take called A. When you take A, with 3/4 probability you go to S2, with 1/4 probability you go to S5. Okay? From S2, there are two separate actions, B and C. If you do a B, you will definitely get into S3. If you do a C, you will definitely get into S4. So there are labels that are added on top of your usual Markov chain. There's a logic for GPL, and it turns out GPL is extremely interesting, that it's a mu calculus based logic, it's a model mu calculus based logic. It is strictly more powerful than PCTL star, so you can actually encode PCTL star model checkers if you can do mu calculus here. And it can be used to also construct model checkers for what are called recursive Markov chains. Markov chain is where instead of just making these kind of automata, like finite automata like transitions, you can actually do push down transitions. But even though the original conference paper appeared in 2002, I believe, and the journal version appeared in 2005, until last year there was no model checker for this logic because it's just too complex. The model checking algorithm given for GPL was 8 pages long, and it had 14 different cases that you had to go through, and it was doing something like analogous to a Fisher-Ladner closure by saying, if this property holds at this state, then do this actions, and there were 14 different cases that you had to go through. There was no intuitive explanation as to why the 14 cases are ordered in this particular way, because each case would say, if the previous cases didn't apply and this condition applies, do this. And there was a huge proof for why all these things should succeed. And here is our GPL model. This essentially captures the essence of GPL semantics. If you look at the GPL paper, again, there is semantics that is given in a short form. And if you just encode the semantics, this is all the semantics is. There are diamond and box, it's the mu calculus based model checker. Right? So here you say that at a state S, diamond AF holds. What diamond AF holds means that there is an action A that you can take after taking that action. There exists an action A, after that action F holds. Box means for every action after A, F holds. Okay? So these are two different kind of quantifiers over actions. And all we have here is simply saying that if there is an action called A from state S, find a distribution of the states that you reach after that and do the models on those states. So it's a very simple encoding, very similar to the EF encoding that we did before. Okay? So the straightforward encoding of GPL model checker, and it turns out that this probabilistic logic way of encoding model checkers is actually useful in being able to encode this kind of more expressive model checker. Why is GPL actually useful? There is more recent work on what is called recursive Markov chains. This work was started, the first paper on this was by Yanakakis and Yachasami in 2005. I think they had a JSCM paper significantly later, 2009, but the first conference paper was in 2005. These are essentially Markov chains where you have boxes which are essentially like calls. So you can think of this as a Markov chain. You can think of this as two procedures, A and A prime. Procedure A has an entry En. Whenever you get to entry En, you toss a coin. With some likelihood, you go to first state. In this state, you actually invoke procedure A prime. Okay? So this box is like an invocation of procedure. These are exit blocks, return blocks. Once A prime successfully ends, based on what it returns, you do certain actions. If you return value 1, you go to EX1. If it returns value 2, you toss a coin and go 3 ways. So it's a significantly more interesting way of looking at problems. It's like a probabilistic program. Right? There are calls and returns. Similarly, A prime has two different calls. Whenever you do A prime, you can end up calling A or you can call A prime again. Recursive. This is a recursive Markov chain. And there is work on model checking recursive Markov chains. But it turns out that if you have a GPL model checker, you can actually use that to model recursive Markov chains. This we didn't know before. I wish we had known this 10 years back when we were doing work in push-down systems and verification of non-probabilistic push-down programs. If we knew that we could encode them in new calculus and be done with it. This is actually a neat encoding, that's why I want to take a little time to tell you this. That all you do is for every time you encounter a call, you add a call edge from the calling site to the entry point of the call procedure. And all the returns, we kind of turn them on themselves because after return you don't do anything. But instead of using the return, what we do is introduce two new edges called return edges within here, R1 and R2. Of course, if you just look at it as an automaton, it makes no sense to do this because it looks like what we do from En is to go here, make a blue edge to go here, and there is no, it looks like from here you can directly take the red edge and go here. But these are not the kind of paths we are looking for. We change the formula that we are looking for. If you look for reachability, let us say I want to find out what is the likelihood I will reach Ex1, I can write down a formula like this. The likelihood of the property of reaching Ex1 or EI in general is that EI is possible in the current state, or after some arbitrary transition I can get to EI in one step, or I can make a call. This call returns with X1, and then I can take the corresponding R1 and go to XI. So the return value, the matching between calls and returns is handled in new calculus here. Call returns with 1, and then I take the return edge 1 and go to XI. Or call returns with 2, and I take the return edge 2 and go to XI. And now if I have, once you use this formula, this is simply an RPLTS, a reactive probabilistic transition system. I can use my GPL model checker and model. So this is something that we can do with just because we have the technology to actually look at probabilistic. We have a technology to actually encode really complex inference systems and do a good job of actually inferring based on these systems. Let me skip over MDPs, not very relevant. I will go into so the kind of things that we are currently looking at are kind of sampling-based methods. That now that we have a way of inferring exactly what the probabilities of these runs are, when the systems are very, very large, it's very hard to kind of scale nicely. So we're looking at sampling-based methods for approximately inferring the probabilities of the systems. The question is how these methods actually relate to statistical model checking, which are also sampling-based techniques, but underlying systems are not probabilistic. So this leads us to the kind of work that we would like to do from here. So as I said, I would like to be able to figure out what the relationship between whatever we have done so far in probabilistic model checking is with related to statistical model checking, which is simply sampling of non-probabilistic systems. There is also something very interesting that we can do that, for a lack of a better word, I call this stratification. The systems that I've encoded so far, the outcome of one probabilistic process can determine the distribution or outcome of another process. But it is not possible for us to write programs where we inspect the likelihood of some outcome and then change the probability of how the system actually evolves. So there is some kind of stratified behavior that we have here. A prob query does not actually it doesn't actually have a probability mass to it. The prob query simply has a number, and it's a non-probabilistic number. We would like to be able to explore what it is for a system where, for instance, when you're driving a car, when you make a judgment that I'm going to take this particular road, you estimate this is the amount of time it's going to take me to reach there. But once you have taken the decision, that changes the underlying likelihood of how we will actually reach. And we would like to be able to model that as well. So there are interesting things that we can do with this. And of course, all this is not my work. This is work with a number of people, past and present. And my thanks to them for doing all this work so that I can come and talk about it.